Okay, good morning everyone. My name is Gordon Ledford, and I found myself recently in a situation where I needed to sort of defend or advocate the case of using a non-traditional computation platform for evaluating neural models, whether we were shooting for simulation or implementation, either analog or digital. And so what I wanted to do was kind of look for some supporting information in terms of work other people had done. And what I really wanted to find was Verilog code that I could just compile and run and say, hey, look, someone did this and it was worth doing. So my first search didn't really turn up anything very promising, but this semester I was able to come up with something that was a little bit closer. So we've got a paper here, dynamical digital silicon neurons, and I really don't know what's up with the word dynamical, but there it is. This was a conference paper, and so it was kind of interesting. The basic problem that they want to solve is they want to generate the output of a neuron. Okay, and so this is just an example of the kind of thing that you can get out of a neuron. And what we're looking for is a way to get a digital circuit to basically run through that simulation or give us a way to generate that waveform data. So one way you can do that is with a mathematical model. There are lots of those. A kind of a popular one that's a little bit relatively more recent is the Izhikevich model. This is a pretty simple model in that it's only got a couple of state variables you have to evaluate, but it's numerical. So we have to do some number crunching to actually do this thing. Now this is actually the update equations. V prime is the next value of V, U prime is the next value of U. We actually have also a clipping condition. So this gives us some nonlinearity. It's what limits the peaks of those spikes that you saw earlier. The variables in there, V and U, those are our state variables, and V is what actually represents the output of that waveform. The other things that we've got available to us are the synaptic input, which is I, that's the stimulus that actually makes it respond by generating that waveform. And then we've got a couple of constants, A and B, that are used to tune the behavior of the model to be different types of neurons. So we're going to see examples of that later, I think. What this paper did was take that model and cast it in the form of an implementation on an FPGA. And they used fixed point arithmetic. They did some other things like scaled their equation coefficients and so on to keep it simple. There were some complications they had to deal with, like multipliers take an extra clock cycle compared to adders, and that there were only a certain number of multipliers available. But you could implement those update equations relatively straightforward. And you'll notice it's basically a combinational problem, but they chose to actually do some pipelining in there, and that's what the little dashed lines are indicating. So they had equations for both the V and the U expressions that needed to be updated. Now, because they had a pipeline, they needed some structure in there to kind of maintain this, and the other thing that they actually did, since they had to do pipelining anyway, was they actually put multiple neurons through the same pipeline. So they're updating the state of several neurons, and that's what the U store and V store are all about, is the states of the neurons that they're updating. Now this got into a bigger system so that you could actually simulate a whole neural system. So you had to actually deal with the inputs, the dendrites, the interconnections, all that kind of good stuff. But that's what they were able to do. They used, for us, it would be a relatively older FPGA at this point, and they were able to set up 32 blocks of neurons with 8 neurons on each block. Their limiting factor was the number of multipliers on the FPGA, and because of the limited number of multipliers, they wound up having to multiplex the multipliers between the U and the V pipelines. The pipelines were static. In other words, those expressions, they're like not just hard-coded, that was the hardware. And they kind of had to manually figure out where it was they needed to multiplex the multipliers And the other thing is all of the neurons on a block share the same characteristics, like the same values of A and B. The other thing that was kind of a factor is they had a fixed time step, which they didn't really talk about very much. My observations here, they actually used a digital approach, an FPGA, to do the simulation of a neural model that was, analog in kind of its underlying character. They point out that there are obvious advantages between software and analog versus digital. At the time, another note that they made was that neural prostheses, the things that you would maybe use to help someone who's been injured, were generally implemented with microcontroller-based techniques, which I thought was interesting because it's very sequential, not very parallel. And I would actually be curious to kind of go back and look at some of those if I could. Anyway, that was it. Thank you for your time. Any questions?
Interesting, strange one for you. Why was it 18-bit?
I think that was the limit of what they had available on the FPGA. I think that was their multiplier width.
Yeah, the XC3s had 18-bit multipliers
Right.
built into them.
Yeah.
So,
Yeah.